So yeah, today I will talk a bit about our recent work on robust model discovery with SINDy and Ensemble learning. And this was work done with my collaborators back at the University of Washington with Nathan Kutz, Bing Brunton, and Steve Brunton. All right, so in the next hour or so, I'll mainly, 40 minutes, this is a shorter one, yeah. So in the next 40 minutes, I'll mainly talk about robust model discovery. So how we can learn or discover differential equation models from limited and noisy data. And the main method that we use to learn these equations is called SINDy, or sparse identification of nonlinear dynamics. And in our recent work, we extend the SINDy method with ensemble learning to make it more robust in the high noise and low data limit. All right, so first I will introduce the SINDy method and the ensemble-SINDy extension. And then I will talk a bit about two applications that I am currently working on that are shown here on the slide. So on the left, you can see an airborne wind energy simulation of a flexible wing that I developed during my time at ETH Zurich. And on the right, you can see a flapping wing robot that the collaborators at MIT designed. And in both of these examples, it is quite challenging to derive accurate and computationally efficient models for prediction and control. So basically, we're trying to apply our SINDy methods to improve modeling and control of these systems. So these are ongoing projects, but I want to talk a bit about them to give a better idea on how our methods could be applied to these challenging fluid flow and fluid structure interaction problems. All right. Yeah, so as I just mentioned, I am broadly interested in modeling, design, and control of flight systems. So on the right here on this slide, you can see a couple of problems that I'm working on, such as the airborne wind energy system and the flapping wing drones from the first slide, and some other projects on the bottom videos where you can see different types of morphing wings that we developed. So basically wings that can change their shape to different flight conditions. And we look at different applications for these morphing wings, such as, for instance, UAVs, like the one in the middle could, for instance, be used in agriculture or surveillance. And the concepts on the bottom are, for instance, used in a renewable energy system. So these are types of problems that I'm currently dealing with in my work. But then on the left side, more broadly, you can see different applications in aerospace and renewable energy industries, where the systems that are shown here on this slide, they all work in fluids, and the flows and structures, they tightly interact. So for instance, you can look at the large flexible wind turbine blades or high aspect ratio wings of aircraft and drones. So not just in my work on morphing wings, but in general, there are lots of applications across these industries where we can have a large impact by improving our understanding and also improving the ability to model and predict fluid flows and flow structure interactions. Now, the challenge with better understanding and improving our capability to model and control these systems is that the dynamics of these systems are usually nonlinear, multi-scale, and high-dimensional. And additionally, in some of these applications and problems, we have to consider the tightly coupled fluid and structure interaction. So we're dealing with multidisciplinary problems. And yeah, that is basically what motivates our work. So we're interested in developing modeling and machine learning methods to improve the understanding of these fluid flows and fluid structure interaction. And we want to accelerate the design and control of these aero and renewable energy systems using machine learning. Okay, so that is basically the goal and overview of our work. So how can we use machine learning to improve modeling and control of aero and renewable energy systems? Now, in most industries, but in aeronautics especially, it is crucial that the machine learning methods or the machine learning models that we use are interpretable and generalizable. So we basically want to work with models that are interpretable, such as, for example, Newton's F equals ma. So a compact model with three terms. force, mass, and acceleration, we can understand, interpret, and discuss this model. And second, the models that we learn should also be generalizable. So again, F equals ma is the perfect example. It's accurate here on Earth, where the apple is falling off the tree, but it's also accurate to predict space missions and landing a spaceship off the moon. So F equals ma is a great example of an interpretable and generalizable model. Now, as I said, in aeronautics, but also in other safety critical industries, learning models that are interpretable and generalizable is super important. So, for example, if you want to use our models in passenger aircraft, flight controllers, or drones and autonomous robots with humans in the loop, these models need to be interpretable before we deploy them. So we need to exactly understand what they do. And they should also be generalizable. So they shouldn't overfit to the data that we train the models on, but they should ideally be accurate also outside the training data to unseen conditions. Now, this principle of interpretable and generalizable models is an old principle, and we didn't just start thinking about this recently. So for instance, Einstein already said that everything should be made as simple as possible, but not simpler. Or this is also known as Occam's razor. So the models that we want to learn and use should be as simple as possible, but no simpler. Now, in our case, when we want to learn models purely from data, as simple as possible, but not simpler, can be interpreted as learning low-dimensional and sparse models that are accurate, but don't overfit the data but they basically don't overfit to the training data that they were trained on. So basically, we want to learn accurate models that are described by as few degrees of freedom as possible, and that have as few terms in the equations as needed to describe the dynamics. And one method that can learn or identify such low-dimensional and sparse model is the SINDy method. So the whole idea behind the SINDy method is basically to learn these sparse nonlinear dynamical system models, so accurate models or equations that use as few terms as possible to describe the data they are trained on. All right, so this is the basic idea. We want to use machine learning to find interpretable and generalizable models. And in our work in particular, we want to use these models to better understand fluid flows and fluid structure interactions, and then use these models to improve the design and control of aero and renewable energy systems. All right, so this is basically the goal of our work. And in today's seminar, I want to give a broad overview of these methods and how they can be applied to challenging problems in aeronautics. So first, I will introduce the SINDy, or sparse identification of nonlinear dynamics method. I'll introduce the main challenges and some main extensions of the method. So the method was, I think, introduced 5-6 years ago. And over the last years, the method has been improved significantly. And then in the main talk, the main part of the talk, I will basically introduce how we can use ensemble learning with SINDy. So I'll talk a bit about how this can improve the noise robustness in the low data limit, and also how ensembling can be used to efficiently quantify uncertainty and also perform probabilistic forecasting. And then I'll talk a bit about how we can use this ensemble-SINDy method for efficient exploration using active learning. And then in the final part of the talk, as I mentioned, I will introduce some ideas on how we can basically learn models of flapping wing robots, and also on trying to use SINDy for the airborne wind energy simulations. So these are both projects, as I mentioned, that are ongoing, but they should give an idea and outlook on how the methods that we developed could be used in different aero and renewable energy applications. Okay, now, before talking about these different applications that I'm working on, let me start with introducing the SINDy algorithm. So the method was published in 2016 by Steve Brunton, Josh Proctor, and Nathan Kutz. And the goal of the method is, as I mentioned before, to learn interpretable and generalizable models from data. So it's basically a machine learning method, that can extract dynamical system models from time series data. So if we, for instance, would have a pure time series data set, for example, measurements X, Y, Z over time from the Lorentz system, so that would be the butterfly attractor that is shown here on the left. The dynamical system that we would learn would be of the form of an ordinary differential equation. So given the data, we will basically take a modeling assumption that we want to learn an ODE. Now, another example, if we would have spatiotemporal data, for instance, snapshots of the velocity and vorticity fields over a time of the flow past the cylinder, so shown here on the bottom left, where you can see these different snapshots over time, the dynamical system model that we would want to learn would be of the form of a partial differential equation. And then what SINDy basically does is that it can identify sparse differential equations that best describe the time series data. So we can, for example, learn the exact ODE of the Lorentz system dynamics, or for the flow past the cylinder, we can learn the PD, like the Navier-Stokes equations with the sparsest or basically smallest number of active terms in the differential equations that would accurately fit the data. So the main idea is that we don't just want a model that best fits the data, like let's say a large neural network that could potentially fit our data very accurately, and which could potentially also be used for accurate forecasting, but we want to learn a sparse or compact equation that best describes the dynamics, which we can understand and interpret. And this is basically what the SINDy algorithm does. Okay, now first to introduce the algorithm in detail, I will use the Lorentz system dynamics data. So I will first introduce how we can identify ODEs from data. Okay, so how does the method work? So for this synthetic Lorentz system data set, we would pretend that we only have access to measurement data, but we wouldn't know the underlying dynamics. So here we would basically measure a time series of the state X, Y, and Z, but we wouldn't have access to the ODE that actually generates the data. So shown here on this slide, the right three columns are the time series measurements, and then we would assume that we can calculate the time derivatives of the state. So basically the three columns on the left would be X dot, Y dot, and Z dot. And this is quite a strong assumption that we can actually accurately compute these derivatives. So in this example here, it is no problem to get these derivatives for our clean synthetic data set. But when we think about noisy experimental data, this can be very challenging. Then in a second main step, we build a library of candidate nonlinear terms that we think could best describe the measurement data. So for example, we can use a library of polynomials. In this example here that I show, for example, polynomials up to fifth order. And all the gray columns, so the additional terms in our library, we can basically directly calculate from our measurement data X, Y, and Z. So we basically augment the right-hand side and build a library with nonlinear terms that could be used to describe the time derivatives on our left-hand side. And now the goal of SINDy is to then basically find the fewest active terms in the library that best describe the dynamics. So we want to find an equation that best describes the three equations X dot, Y dot, and Z dot. So basically, I want to find the fewest columns of my library that add up to X dot, Y dot, and Z dot. And the way we do this is by a sparse regression. There are a lot of different optimization algorithms that can basically efficiently solve this sparse regression problem. Most of you might be familiar with the Lasso algorithm, but what we mostly use is a sequentially thresholded least squares algorithm. So basically what we do is we sequentially solve a least squares problem and then hard threshold coefficients from our least squares solution that are smaller than a sparsification parameter. And this parameter basically defines the trade-off between accuracy and complexity of the discovered model. So we basically solve a least squares problem, threshold small coefficients, and then we perform the least squares again and again on the smaller library until we find a sparse SINDy model. So what we learn basically with SINDy is then the structure of an ODE, so what terms are active in the ODE, and also the coefficients of the ODE that best describe the measurement data. So on the Lorentz system example here, when we look at the results on the top right, we can see and interpret that, okay, so for instance, the first state or the x dot equation is linear in x and y, and the y dot and z dot equations have quadratic nonlinearity. So we basically get a sparse model that we can interpret and understand. And on this synthetic data set, we can see that we can actually identify the two equations that were used to generate the data, which is really nice. So basically, with the SINDy method, we can identify a sparse ODE that can accurately describe the data it was trained on. Now, apart from identifying ODEs, a very important extension of the SINDy algorithm was introduced by Sam Rudy in 2017, where they extended SINDy to identify PDEs. So for identifying PDEs, if we have spatial temporal data, so for example, unsteady fluid flow measurements, we can use SINDy to find and build a PDE that best represents our data again. So shown here on this slide, if we, for example, measure the vorticity field omega and the x, y velocity fields u and v in space and time of this flow around the cylinder, we can try to identify the PDE using SINDy. So basically, just like in the ODE example, we would also build a sparse regression problem where we would try to represent the time derivatives of some quantity. So in this case, the time derivatives would be of the vorticity as a sparse combination of library terms or candidate functions that would contain now partial derivatives and nonlinear products of partial derivatives. So basically, we would compute, again, all of these gray columns by computing partial derivatives and nonlinear cross terms. And we would then try to find, again, similar to the ODE case, the sparsest combination of these terms that are equal to our left-hand side to the time derivative of omega. And so when we apply this sparse regression, we can actually learn purely from data that, in this case here, for this data set, the Navier-Stokes equation are the dynamics that are the sparsest and most consistent with the data, which is really nice. So with the SINDy, we can basically also identify PDEs. Okay, now since these first papers, we have seen lots of extensions and applications, especially in fluid dynamics and aeronautics. On this slide, I just want to give an overview of some cool applications of SINDy. So for instance, the vortex shedding past the cylinder from the slides before, challenging model discovery problems in aeronautics on shockwave dynamics. A lot of other cool examples in fluid dynamics. So this is mainly coming from the group of Steve Brunton. Really cool work by Jared Callahan, these two papers, plasma dynamics, or very recently also discovering PDEs from experimental turbulent fluid flow measurements. So lots of challenging problems are involved with SINDy. Now, in many of these examples, the standard SINDy method that I introduced in the slides before would probably not be able to identify a sparse model, especially for experimental data sets. So as I said, computing the time derivatives with noisy data is quite challenging. So there are quite many challenges in applying SINDy to these real-world problems where the data sets are basically limited and noisy. So in the next couple of slides, I want to discuss some general challenges and extensions of the SINDy method, and then introduce our recent ensemble-SINDy extension, which is robust to noise, and which can also quantify model and parameter uncertainty due to noise and limited data. Okay, so one first problem or challenge that is not directly related to the quality of the data, but that is very important is how do we actually know if we measure the right variables? So is the coordinate system in which we measure actually appropriate to finding sparse dynamics? Or are there maybe better coordinates where the dynamics might be represented with fewer terms? So in the case of the Lorentz system, we only have three states, but in many high-dimensional complex dynamical systems or data sets where the governing equations are unknown, it is not quite clear which coordinates would admit a sparse dynamical system model. So in a recent work by Kathleen Champion and collaborator, they extended SINDy to simultaneously discover coordinates and sparse nonlinear models using autoencoders and SINDy. So basically, the autoencoders enables to discover reduced coordinates from high-dimensional data, and in a joint optimization, SINDy identifies the sparse nonlinear model in these reduced coordinates. So the optimizer basically jointly minimizes the autoencoder reconstruction loss and the SINDy error. So this is a really powerful extension of SINDy and addresses a main limitation of SINDy, which is basically assuming that we are already measuring our data in a coordinate system that allows a sparse representation of the dynamics. And the second challenge is related to the measurement data itself, what I mentioned before, and the actual quality of the data. So how much data do we actually need, and of what quality should the data be? So when we, for instance, think about experimental data sets given certain sensors that we select, the data is usually noisy and limited. So we often don't really have the luxury of large and clean data sets, such as, for example, the ones I used in the synthetic Lorentz system example. And over the last 5 years, a lot of work has been done dealing with the data quality issue. And this is also where ensembling can basically help to improve the robustness of SINDy. When we only have, limited and noisy data sets. But this method I'll introduce basically in a minute. But before that, another extremely useful extension of the SINDy algorithm is the weak or integral form of SINDy. So basically, in this weak form of SINDy, the data or the time series trajectories are subdivided in smaller domains, and then integrals over these subdomains or control volumes are considered. And basically, by doing this, we can avoid calculating the time derivatives of the noisy data. So this is an extremely useful extension of SINDy, where we integrate the noisy data over control volumes to avoid computing the time derivatives. Okay, then the third big challenge is the optimization method, which is basically at the core of the method. So there are different strategies to solve the sparse regression. And as I mentioned, an effective method is sequentially threshold at least squares. So basically, we sequentially solve the linear regression, and then we hard threshold small coefficients. And we do this sequentially over and over again. Now, the challenge here is that we constantly have to balance model accuracy with sparsity of the model. So basically, how accurate should the model be versus how many terms we keep in the model. And ultimately, we want to set as many terms to 0 as possible for interpretability, but we also still want to have a decent model accuracy. So we have to basically tune this sparsity promoting hyperparameter. And one idea to deal with this is to combine information criteria with SINDy. So the idea there is to identify several SINDy models with different levels of sparsity, and then to compute an information criteria score for the different models. So we can basically calculate a score based on the model prediction error and the number of active terms in the model. So this is a great way to basically tune the model hyperparameters by combining SINDy with information criteria to get the best trade-off between model accuracy and complexity. All right, so we see that there are many challenges with using SINDy and identifying these sparse model from data. And in this slide, I was hoping to give a flavor of how different extensions of the SINDy method can basically help tackling these challenges and help improving the applicability to real-world noisy data. Now, in our recent work, we wanted to explore if we can further robustify SINDy in the high noise and low data limit, and if we can find a computationally efficient method that would provide us not just with a single deterministic model, but also identify model coefficient uncertainties. So basically a method that can quantify the model and parameter uncertainties that could then be used for probabilistic forecasting. And our idea to do this was to explore ensemble learning methods. And now I assume most of the people are familiar with these methods. So the idea behind ensemble learning is basically to combine predictions from multiple models. So instead of having a single model or a predictor, we would basically learn multiple models using subsamples of the data. And for different modeling strategies, it has been shown that basically ensembling can improve the accuracy of model prediction, and it can also reduce the variance of the predictor. So it can basically help to avoid overfitting a model to the training data. And a particularly popular ensemble learning method is bagging, or bootstrap aggregating, which is basically a method where we randomly sample our data with replacement and then train individual models on these subsamples of the data, and then ultimately aggregate the individual models by averaging the outputs of the different models. This is a very popular method that is broadly applied to improve basically the accuracy of model prediction. Now, if we think about identifying dynamical system models when we use SINDy, we usually identify a single model using all the measurement data, or the complete time series trajectory, let's say. But instead, we can also pick data bootstraps to build an ensemble of SINDy models. So basically, several SINDy models instead of just one. So again, for the Lorentz system data, where we, for example, have a time series of length n, we can select n data bootstraps to generate an ensemble of SINDy models. So basically, for each of these bootstraps, we sample m new rows with replacement from the original data, and then we solve n sparse regression problems on these data bootstraps. So ultimately, what we basically do is we identify an ensemble of SINDy models, so several SINDy models using these bootstraps of the data. And then finally, what we do is we use the ensemble statistics to threshold coefficients that are unlikely to appear in the dynamics, and then we finally aggregate a final model. So basically, the idea is that we throw away all the model coefficients that appear less than a certain threshold in the ensemble, and we then aggregate a single SINDy model by just taking the mean, or for instance, the median of the identified model coefficients. And in our paper, we tested a range of different ensembling methods, and we found that robust bagging or bragging, basically taking the median of the identified models, works best and clearly outperforms the baseline SINDy in terms of accuracy. So by applying this ensemble learning method, we show that SINDy can handle noisier data and can still identify accurate models, even if we only have limited amounts of data. And now, apart from robustifying SINDy, what is also interesting about E-SINDy is that we get uncertainty estimates of the model coefficients. So we don't just get a single SINDy model, but we can actually get a distribution of model coefficients. So we can look at the ensemble statistics to quantify the uncertainty of the model coefficients. So basically, what I plot here on the left, again, for the Lorentz system, are the model coefficient distributions for the identified ODE of the Lorentz system dynamics, which is basically a measure of the uncertainty of the identified model parameters. And then we can also look at the inclusion probability of the coefficient, so how likely a coefficient will appear in the ensemble of SINDy models. And here we see that basically the terms that we expect to be active have a high inclusion probability, so they are shown in bold. So basically they appear in most of the individual SINDy models in the ensemble. So basically with ensembling, we can quantify both the SINDy parameter and the model uncertainty. And then what is also very interesting with this method is that we can run ensemble forecasts, basically provide prediction confidence intervals. So we can sample models from our ensemble and then basically run multiple predictions using these different methods. And what is particularly nice about this method is that E-SINDy can basically identify these models and summary statistics in only seconds. So it's computationally very efficient, and this is quite an advantage when we compare it, for example, to other methods that can provide uncertainty estimates, such as, for example, let's say Bayesian model discovery that would use MCMC to perform model identification. So for these type of model identification methods, like the Bayesian methods, they usually take several hours of CPU time to identify even these simple Lorentz system dynamics. So this is quite an advantage of E-SINDy that only takes a couple of seconds to identify these models here. Okay, so to summarize, the E-SINDy method basically robustifies model discovery, and it is a computationally efficient method to identify these probabilistic models, which can be extremely useful in applications where fast or real-time estimation of models is useful or necessary. And in a very recent work with my collaborators at University of Washington, we also started discussing the connection between these empirical model coefficient distributions using E-SINDy with Bayesian methods. And Mars Gallo, an amazing PhD student at University of Washington, basically showed that E-SINDy is asymptotically equivalent to Bayesian SINDy, so we can basically perform valid uncertainty quantification with a statistical guarantee using E-SINDy. And he just put the paper on the archive. I added the link here, so if you want to check it out, it's a really cool paper from Mars and collaborators at University of Washington. Okay, then one thing that is also really cool with this method is that we can also use these probabilistic models for active learning. So can we efficiently learn a model when collecting data is time-consuming and expensive? And in our recent paper, we basically show a first idea on how we could do this. So in the example in the paper, we again look at the Lorentz system, and we want to understand if we can use E-SINDy for efficient exploration. So how can we collect data such that each experiment or simulation maximally informs our model discovery process? And our idea to basically achieve this was, so to efficiently explore and maximally inform our model discovery was to basically use the ensemble statistics of E-SINDy iteratively. So basically, instead of just running a single set of experiments, we use the ensemble statistics to find and explore high uncertainty regions in the state space. We basically do this by iteratively identifying E-SINDy models. So we start with collecting a small amount of randomly selected data to identify an initial E-SINDy model, and then we select a number of random initial conditions and compute the ensemble forecast variance for each initial condition using the current E-SINDy model. So basically shown here on the slide, you can see on the left 5 random initial conditions and ensemble forecasts again for the Lorentz system. So basically we use our ensemble model to estimate these trajectories for different initial conditions, and we can then compute the variance of these different E-SINDy forecasts, and then finally we only sample the true system with the initial condition with highest variance. So basically we sample the location in the state space with highest model uncertainty, basically performing the next experiment where our model is most uncertain. So basically the ensemble statistics from E-SINDy can tell us how we should explore and sample data to maximally inform our model discovery. And basically shown in our paper that by using this active learning approach with SINDy, we can actively reduce the variance of the SINDy model coefficients. So we can basically squeeze the PDFs of the model coefficients using less data. So shown here, you can see how we can reduce the variance of the SINDy model coefficients by this active learning. So basically the dark plots show the PDFs with active learning compared to the more transparent ones for the standard SINDy. And ultimately, basically, this means that we can improve the data efficiency of our model discovery, so we can identify an accurate SINDy model with less training data using E-SINDy with active learning. And this can be, of course, like really useful when running experiments is expensive and time-consuming. All right, now in the last part of this seminar, in the last couple of minutes, I want to talk about 2 applications in aeronautics where we are trying to use these methods. So basically, now the 2 projects are still ongoing. So we only have a first conference paper on the flapping wing robots, but I think it's still interesting to have a small discussion on how we are actually trying to apply these methods to challenging real-world aero and renewable energy problems. Okay, so the first project that I quickly want to introduce is a collaboration that we started last summer when I was still at University of Washington, and we started this collaboration with 2 groups at MIT, with Professor John Howe and Andrea Tagliabue, who are both experts in drone control systems, and with Professor Kevin Jen, who develops these amazing flapping wing drones that can perform agile maneuvering in confined spaces. And basically part of the collaboration was trying to learn discrepancy models of the flapping wing aerodynamics to improve control. So we would basically start with simple first principle models of the drone dynamics, and then try to use E-SINDy to learn the unmodeled dynamics. And we have some first results on identifying these discrepancy models that we basically use in flight simulators to develop flight controllers. And my collaborators just demonstrated different control tests and flight maneuvers of the drone, as shown here on the two videos where the drone basically performs these ramp and circular flight maneuvers. So this is still ongoing work, and we are quite excited to see if we can achieve more agile flight maneuvers using the models identified by E-SINDy. So basically, using E-SINDy to improve the simulators where we train our controllers that we can then deploy in reality. So that's basically the idea, using E-SINDy for discrepancy modeling. Okay, then the second project that we are working on is on airborne wind energy system design and control. So basically, airborne wind energy is this power production technique where we try to harvest wind energy by using tethered fixed-wing drones. That is basically what I show here on the right in this animation. And on the left, you can see a prototype of an airborne wind energy drone that the students developed in a project at ETH Zurich. So these drones basically operate over a wide range of wind speeds and operating conditions to maximize their power production. And we are interested in identifying accurate and computationally efficient models for prediction and control that are basically valid over these large operating regimes. So the whole idea here is that we want to operate these systems 24/7 throughout the year. So over all the different wind speed and flight conditions that such a system could experience. And we are trying to find models that could accurately describe these large operating regimes. So basically what we try is to apply E-SINDy to enable then probabilistic forecasting in these harsh conditions that could be used for robust control and improved production of such systems. And then the second idea that we have is basically a problem where we want to design these systems. And the whole point here, because of the dynamic nature of these systems, is that we have to concurrently consider the wing design and control when we develop these systems. So basically, the control and the wing design are so tightly coupled that we cannot look at them separately. So basically, we found that, and that was worked throughout my PhD, we found that simultaneously optimizing control and wing design can quite drastically outperform sequentially optimized systems. So basically, we're thinking about using fast surrogate models identified by E-SINDy to accelerate the design and control optimization of these systems. So basically, what you can see here is a visualization of such a control co-design optimization of an airborne wind energy system. So concurrently, the optimizer changes the flight mission, controller gains, and the wing design. And on the right, you can then see how the power production, so our optimization objective, basically improves over the optimization. But the problem is that these optimizations are extremely heavy. So we're thinking about improving the efficiency by using fast surrogate E-SINDy models to basically speed up these optimizations. So this would be a really nice application of the method to accelerate design optimization of wind energy systems. And at this stage, we are exploring different strategies to basically incorporate E-SINDy on first simple problems, and then moving slowly towards these full system dynamic models for optimization in a later stage. So this is still ongoing work. Okay, so to summarize my talk, SINDy, the sparse identification of nonlinear dynamics, is a method that can identify sparse ODs and PDs. I talked a bit about general challenges and extensions, such as jointly learning coordinates in sparse models, the weak form to avoid competing derivatives, and also using information criteria to tune hyperparameters. Then I introduced our recent E-SINDy method, which improves robustness and accuracy of SINDy, especially in the high noise and low data limit. And it can identify probabilistic models at low computational cost. And the ensemble statistic can also be exploited for active learning. So basically, the E-SINDy method can robustify SINDy, identify probabilistic models, and it also enables active learning for data-efficient model discovery. And then finally, in the last part, I introduced two applications of the method, or two ongoing works. We're trying to apply the method on challenging flattening wing robots, and also this control co-design of wind energy systems. All right, and yeah, if you're interested in using these methods, you should check out the SINDy GitHub. So it's a really nice repository that my collaborators at UW basically put on GitHub. All the SINDy methods, from the vanilla SINDy to the different extensions, they're all implemented there. It's a bunch of tutorials. So if you have never used SINDy, you just go through the tutorials. So it's a really cool repository where you can learn and then also apply the different extensions to the different types of data sets that you would be interested in. All right, I think, yeah, with this, I would like to conclude my talk. Yeah, again, thanks a lot for the invitation to the seminar, and I'm happy to discuss some questions.
Thank you very much for a nice talk. Yeah, and we already have some questions here. So yeah, one is from Professor Mario Olberger. Why don't you use L1 minimization for sparse identification?
Sorry. It's a very good question. So that's basically how they started in 2016. They first tried with L1, basically regularized least squares would be the lasso approach. But the problem is that you have quite quickly, only with a tiny bit of noise, not really sparse models. So they found out that if they use this approximate L0 optimization with the sequentially thresholded least squares, that they or we get much better results with SINDy.
Okay. Yeah. Okay, let's go. We have one more question. Could you please share your thoughts on how to design the library in SINDy when one variable is substantially larger than other ones? For example, in SIR model, susceptible population can be extremely larger than the other variable, let's say 10 to the power 6 times. Without normalizing y, it will be dominating in sparse regression. If we normalize y, it will be close to a constant. How would you prevent identifying x as a function of y, or population as the function of variable?
Yeah. If it is possible to normalize the variables, I think that would be one approach. But ultimately, I was working with SIR models quite a bit for implementing SINDy with control, and that should actually work. So I should have actually introduced that. That would have been interesting. So I have the GitHub tutorial and the SINDy with control paper for basically systems with external forcing. So that actually does work even if you have these type of data sets. So that is basically possible to be solved with SINDy. So you can check out my GitHub, and there's basically a tutorial on exactly. Yeah, I have also, I think I have the four-dimensional. I looked at the four-dimensional model SEIR, but yeah, basically similar to SIR models.
Okay, yeah, that is good. Yeah, and it was really nice talk, especially it was about high noise and low data limit, which is very much prevalent in many of the experimental data, or if you have very expensive computational model to compute the data for training. So it is very useful, this range that you have addressed. Once again, I would like to thank you very much for your talk. And yeah, I invite everybody, the participants, if you are interested, please refer to his work and also GitHub code. And thank you very much.
Yeah, absolutely. And if you have any questions, you can just email me. I'm happy to continue the conversation offline.